Good morning. I'm Gabriel Dos Reis. I work on C++ at Microsoft. My primary preoccupation at Microsoft on the Visual C++ team is mostly how to make the tool sets around the language much better, how to help programmers write better codes, more robust codes. We use C++ heavily with Microsoft, and we have customers, external customers, depends on C++. They write huge variety of software, and one of the things I do is look at large-scale programming. That explains partly how I got into modules and a bunch of other topics that are related to reliability, programming at scale. So a year ago, I was somewhere upstairs talking about how wonderful modules will be for C++. So exactly a year, I would say, here to report on the progress we've made and where I would like to see the community evolve, what we can do to help programmers, how we can leverage this new facility to build much better software, more robust and reliable software. So my hope is that by the end of next year, we have a formally approved technical specification for C++ modules. But we all know that prediction is very hard, especially in the C++ community. So what happened over the last 12 months? Both at the C++ community level and also in the larger community. So the first thing was, I gave this talk a year ago and got a lot of feedback. And based on that, we actually had a wonderful discussion of the module proposal I had at the time in Kona, Hawaii. So we had CppCon, and a couple of weeks later, we were all headed to Kona, beautiful Kona, Hawaii. And we did discuss the design. There was the wording. It was reviewed by the Evolution Working Group and the Core Working Group, who is in charge of making sure that we don't write nonsense. Made a first pass, review of the wording, and then we set up a telecon review on 7th of December, and that was attended by, I would say, all the core guys, including the compiler writers. All the major compiler writers were on the telecon, and we spent about 2 hours going over the wording, and I got very good feedback that helped me write better spec. That was in the mailing for Jacksonville meeting that happened end of February, early March this year. And at the Jacksonville meeting, Core was satisfied to some extent with the wording, and WG21 as a committee in plenary directed the convener, Herb Sutter, to create a new work item. This is the ISO process to get the technical specification draft up and running. So we had the proposal I had in there as the initial content. Also at the Jacksonville meeting, Richard Smith and Chandler had ideas about how to amend the proposal to support certain scenarios that were not supported by the proposal as it is. I hope you attended, most of you attended, or all of you attended Richard's talk yesterday. The talk essentially is the presentation of what we discussed in Jacksonville. We got a successful ballot, and we have a module TS draft now. Sorry about the rendering. So this is the basis of the technical specification. And since Jacksonville, any new proposal or amendment will have to be made against this document. Okay, so from my perspective, I think this is really positive, and I hope the community understands that the committee is taking modules very seriously. So do the C++ compiler writers. There were a couple of papers that we discussed before we got the technical draft. One was a paper I wrote for the Kona meeting, explaining how the design that we had allowed a gradual adoption, because there's some discussions in the community about whether it was too rigid or not. And as I said earlier, Richard had his paper, Jacksonville. And I encourage you to if you haven't attended, if you didn't attend Richard Smith talk yesterday, I encourage you to watch the YouTube video, which should be up soon. So in terms of implementations, this is serious enough that we want compilers to implement this early stage so that we can test and have feedback to improve the specification and other scenarios that we may have missed. So the Visual C++ compiler from Microsoft has been now trying to stay very close to the spec, modulo bugs or limitations, and so limitations like you all know that the Microsoft compiler doesn't really implement two-phase name lookup or parse into templates. So that was a limitation for the module implementation as well. The good news is that that is being improved, and if everything goes well, in Visual CU 15, which is not the same as 2015, RTM, you should see significant improvements, both within modules implementation and outside modules. So this is really good news. We had a blog post out to describe the implementation, how you can use it in practice. I made another video showing how you can build, how you can consume existing headers as if they were modules, even if they're not modules. That's also instructive. And I have to thank Kenny Kerr, who is one of the earliest supporters and enthusiast adopters of modules. He's written several tutorials on modules. There's one link, and you can see more there. Clang has had what I call module maps that was explained by both Richard and Manuel in their talks yesterday. They have had it for a while. Very recently, Richard put in early support for the module TS specification, so it can parse. It's not doing all semantics analysis yet, but I'm pretty sure Richard will get that as soon as we all get out of this conference. So that's very encouraging. That is at least 2 compilers. I'm hopeful that we'll have a third or the fourth, and that will cover enough platforms, allowing the community to actually test this, not just read the spec, but use it in practice. That's what I want. Where are we today? A year after that talk. I want to take just a minute to So there is nothing new here. Okay, on this slide, there is nothing new. It has been a design. I presented this last year. So apologies if you have seen it too many times, and apology to Reddit if they think there is nothing new. But it is very important to take time to reflect on this. The aims that we have for modules is the first is componentization. It is about software architecture. Yes, build throughput is, we all obsess about that. But here is the thing. If you do not have a structure in your programs, in your applications, then you're not going to get the factor and improvement that you can get. You first need to get the house in order. Right, so componentization is the first aim. Now, you want to explicitly say, this is the boundary of my library, and I take these dependencies on those things. And then you have enough structure to allow the compiler, the optimizer, the linker, to understand all these abstractions, where and how far they go, and across the entire tool chain. That is very important. Okay, I know that build throughput is major, it's a pain point, but we cannot get that if we do not have structure in our libraries program. So componentization is very important. And next is what I call isolation, micro-isolation. For over 40 years, the only technology we have had to construct C++ libraries, programs, infrastructures is sequence of tokens, token streams. And if that is all you have, then you get the brightest minds that will develop very advanced techniques around that, right? Around macros, tokens, but they don't solve the fundamental problem we have with what are my dependencies? Why am I compiling the same things over and over again? What all these technologies around token streams do is they just make more of token streams. They don't reduce that, right? They don't put structure in there. If you want to gain the performance in terms of build throughput, you have to reduce the reach of macros. The other thing is, far too often people say, well, I would like to develop semantics-aware tools, IntelliSense, that kind of stuff, refactoring for C++, but it is hard. Yes, it is hard because there is no structure to token streams. Okay, you cannot parse C++ program if you do not know the full set of values for all macros. Okay, it's just that. So we have to admit that it is important to contain macros. This is it is required. Okay. And then, of course, once you get those two structures, you get to build throughput. We can achieve massive, improvement there. I've seen internally, based on test, improvement going between 10 and 17x, not percent, factor. My personal goal is that by the time we finish the spec and we move into the standard and compilers are supporting modules, attaining factor, build throughput factor, this compile time factor between 5 and 10 should be commonplace. We can do that. It is possible. Okay, so help me get there. The fourth thing, and I probably mentioned this earlier, is having semantics-aware developer tools, IntelliSense, refactoring. If you want to have a safe refactoring, you must be able to understand the code, right? It is not just sequence of tokens, just you have open curly, close curly, and there is a return statement. You must be able to quickly determine whether the local variables you're capturing or the memory variables you're capturing are properly captured and so forth. You ought to have that semantics in there, and it is hard to get if you do not have enough structure. But if you have modules and you let that aside, then you've missed an important opportunity, a fantastic opportunity. The other thing was, originally I thought that it would be possible to get modules for C++ 17, and it turns out that's not possible. Okay, so it's going to be a C++ 17 technical specification, and hopefully into C++, the next version, I don't know where that's going to. And the other thing is, even though the preprocessor is a pain, it is not a goal to replace it or to improve it. Just leave it alone and focus on getting the structure into people's program. So what is a module? Essentially, you have a collection of source files. And then you put a boundary, what we call the modules interface. You have a collection of declarations. You say, well, types and functions, the variables, constants, these are the entry points into my library. Okay, it's my component. Okay, a module has it's a set of source files, right? So you can have several CPP file or CXS file, whatever you call them. This is not Java class files, right? It is not one module, one source file. You can have one source file if that's what suits you, but you can spread the implementation of a module over several source files. We must be able to refer to modules. So modules have names, and arbitrarily I propose a dot notation for modules. The dots do not mean anything at this point. It's just symbolic names that we give to modules. Concretely, how does that look in code? So here you have a consumption. To consume a module, it's extremely simple. So on the left-hand side, I import std.io. That's just me making up a name for modules that I created, and essentially containing out streams and that kind of stuff. And I have a module that provides me data structure for date. And usage consumption of module is extremely simple. You remove your hash includes and you replace that with import. Done. And the rest of the code look basically the same. It's an explicit goal to reduce syntax. I know that it is an eternal debate in the C++ community. Every time we get a new feature, we want to be very explicit about it, right? To make it show in the code that this is new. I am on the side that tend to minimize emphasis on syntax. I think it's the right thing to do. After a while, once you know modules, then it just becomes a distraction. On production side, it's very, very simple, right? I import std.io string, and I have already data structure for reasoning month, and now I'm going and declare my module. So when you see module, some name, dotted name, followed by semicolon, that's the module declaration. It says that from there on till the end of the source file, everything that is not exported is owned by that module. Ownership here means that if you have a different module that define something that's not exported but with the same name, same type, there is no clash, there is no ODR violation because they belong to separate modules. So we call that purview of a module. And the definition of exporting a type or a function is extremely simple. Just seek the keyword export in front of the declaration, you're done. So this is another way to illustrate my emphasis on minimal syntax. And the other thing is, from the working programmer's perspective, there is no new name lookup rules to learn, and that is by design. And you're done. So you have 3 keywords: module, import, export, and that's it. Okay, so behind the scene, as language designers, we try very hard to fit all the things in there so that you, as programmers, focus on the architecture of your software, write solid program, and not having to worry about, do I remember the rules correctly? If you know C++ today, then you're done. Okay, the only rule you need to know is how to define, declare a module, how to import a module, and how to export. And all of those are extremely simple. They don't require arcane syntax. So, from the working programmer's perspective, modules are isolated from macros. Like I said earlier, if you producing a module. It's just an example here. And I import Stud.io. And for some reason, Stud.io in its own internals or interface, whatever it is, define a macros. Then that macros doesn't leak into the importing source file, importing translation unit. This is by design. Similarly, if in the source file that contains the interface of module, you define a macro, that macro doesn't leak out. Okay, have complete isolation. That's how the spec is written today. If you attended Richard's talk yesterday afternoon, you saw examples of how suggestion for handling export of macros. The community is still debating that aspect. When we talk about ODR, now ODR comes free. There's only one place that an entity is defined. The existing standard text has obscure, multiple page description of the ODR. It is obscure and long and arcane only because we don't have an adequate way today in the standard to describe what a module is. Okay, so we talk about tokens, sequence tokens, name lookup, finding the same thing. It's arcane. But once you have modules, then the notion of ODR becomes very simple. There's only one place where it's defined. You don't have to worry about tokens being compared and so forth. The other thing is when you import a module, the compiler doesn't. It is not text processing the way you have hash include. Hash includes, the compiler goes and locates the source file that contains the definition and tokenize, parse, and instantiation over and over. With the imports declaration, what happens is the compiler has internal way of mapping module name to on disk persistent representation of module interface, and if find it and load something, say, usually just bring in names. And if you do not use any declaration from that module, that interface, it doesn't get processed. So you pay only for things you use. This is something that C++ has as an ideal. You don't pay for what you don't use. Today, we don't have that. Today, we hash header files. You pay for things you don't use because the compiler has to process everything. Okay, also for debuggers, for example, it helps, right? Whether you're on Unix, Linux, have the dwarf format, or your Windows platform, we have PDBs. You'll notice that the debug information for a certain component that I use frequently gets duplicated, right? You don't need that duplication anymore. The compiler understands that, just a reference to that thing. So it's another place where it gets improvement from the language when your toolchain understands everything from end to end. As I said earlier, there is no new name lookup rule for the working programmers. If you're compiler writers, you probably need to understand one or two things, but it is not new. Okay. For the working programmers, you don't need new name lookup rules. I don't know how many we have. I've tried to count them. I didn't succeed. I asked Core. They couldn't tell me exactly the exact number. So just stay away from there. The other thing is that not just because we have modules means that we will never again have header files. We will have header files, and they will continue to be there. So the design is such that they work together. And of course, build time is faster. Just to summarize this before I move on to the next topic. For the working programmers, right, devs, when you get modules, how to use modules effectively, the rules are extremely simple. If you have to deal with header files, put the includes first. Next, write the imported modules you need. Next, start the definition of your module. And then you can export things. It is extremely simple. You can even write tools to enforce this style. It is effective. Okay, we have been using this style within Microsoft, where the groups were most eager to adopt modules in product group. Okay, so I have code source there that illustrates what I wanted to touch on. Okay, for me, this basically represents the past, right? No, we've got Clang and MSVC trying to get module implemented. They're all very serious about implementation. We have guides in place about how to use modules. The next thing is, how do you effectively use modules? Where are we headed? So far, the discussions have been on modules as language feature. That's great for compiler writers and for educators. But in practice, people use libraries. And one that is very important is the standard library. We haven't had any discussion about the standard library, what's going to happen. Are we going to turn header files into modules in one-to-one mapping? I would like here to suggest to start a discussion, and I'm not known to be associated with the library working group or library evaluation working group. So this is just a way to start a discussion, and I will take any other suggestion. So the first thing is, I would like the community and the committee to start thinking about how are we going to present standard facilities to programmers as modules. Today, we have a lot of header files, and historically, they have been defined in such a way that they minimize contents and dependencies and all kind of stuff. For example, if you use IOStream has dependency on strings has dependency on some other stuff. So the committee introduced another header file, IOSForward. All it does is just to forward declare a bunch of classes so that you can break this dependency. To some degree, that's an implementation detail, but somehow the standard has to say something so that people can write the same code. I think we should present standard facilities around logical content, not implementation details thing. So, for example, I wouldn't suggest that we turn every header file into standalone modules. Here I have concrete suggestion. I would say, everything that is really STL, the standard template library, as originally defined by Alex Stepanov, becomes a module on its own. So that means all the containers, all the algorithms, iterator, and a bunch of other stuff I can't remember from my top of my head, become just one module. I call it stud core. The name is just placeholder. Please don't focus on it. But the idea is you have that logical thing. If you're dealing with containers, you have to use the algorithms. If you're using the algorithm, most of the time you need the iterators too. So you shouldn't have to write a lot of import statements just for that. One of my favorites is the file system that finally got in C++ 17. I suggest that one to be a standalone module by itself. Same for regex. But then we talk about concurrency. And concurrency, again, it's a cluster of things that makes concurrency. So I suggest that. This is not a requirement. This is just to start a discussion. I want to see the community start a discussion about how we are going to present the standard library. I know we need to start that discussion very early on. So to help with that discussion, the Visual C++ compiler would be shipping this in Visual VS 15, which is not the same as Visual Studio 2015. The next version of Visual Studio timeframe. I don't know exactly when that will come out, but most likely next year, early next year. I don't set the dates. So we can experiment with this idea and get concrete feedback based on actual usage. Okay. So that was library. On the language side, I also like us, the community, not just the community as a whole, to take a hard look at certain rules that we have enjoyed for the last 30 years, and that kind of either conflict or made redundant with modules. So first is, here's a typo on the slide. So when you define a constant in C++, the key thing is actually missing is export. It should read export const st max path equal for 4096. There is this rule in C++ that says that if you declare something const, unless you put xn in front of it or it's a static data member, then it implicitly acquires internal linkage. Clearly, that conflicts with exporting a constant. But this is something that the compiler will handle for you. So we need to change the language to deal with this. The other one that's more interesting is the notion that private members of classes shouldn't leak outside. So I suggested this rule a year ago, and it didn't attain consensus. So I went away, shut up, and but as we have been using modules internally and trying to systematically produce module metadata out of header files, we've come across patterns like this where you have a library, you're trying to define a module M, and then the existing code, what it does very well is to put some implementation details in an unnamed namespace. And there are various reasons why you would like to do that. For example, you like to, take advantage of, optimizations by the linker who knows that if something, if vtable or something else has internal linkage, they can do very simple inlining because nobody else is doing something messy with it. But in general, it is a good practice to put things that shouldn't escape from the current translation unit, put them in unnamed namespace, and then you export a class S that has as private member a data member, non-static data member of that type. That becomes very tricky to explain what the semantics should be. Clearly, that should compile, but if you try that on the Microsoft compiler, I think it doesn't. I haven't tried on Clang yet, but since Clang exports everything by default right now, it is not. It doesn't implement what we would like to see. So imagine that another source file module define a new source file, a class called impl in the same namespace. Remember that namespaces span across modules and translation units. Well, there's going to be a clash between those two classes that's supposed to be distant, right? You can try to find it to make it not clash, but at the end of the day, it is hack over hack and it's brittle. There is no reason why a class impl that is private to translation unit should be visible outside module. This has caused a lot of grief, and I'm suggesting that the community, the C++ community, not just the community, but the community at large, consider this, think about it, and if it makes sense to you, please talk to your representative, talk to your compiler writer, and try to help them understand that perspective. So something that's very important is, so the module design is where we want to be, let's say in 5 years. And we're here today, we need to get there. And how did we get there? It's a transitional path. And there's a lot of discussions about whether the current design allows transitional path. And the answer is yes, it does. And it's not just the bottom up. It doesn't do it in a way that forces you to start with the leaves of your libraries and bubble up. You can do top down. You can just decide that, well, from that if in the include path, I'm going to decide that the boundary of a module start there. You could start there, but you can also start there. Okay? And we have tried this in practice. The video that's, entitled Why You Should Try C++ module explains how this is done in the Microsoft compiler. And I do hope that the implementers community eventually coalesce around a common pattern that we can recommend. Doesn't need to be part of the standard. It could be a technical specification where we say, oh, this is what we recommend as transitional path, right? This is in the spirit of what Richards was talking about yesterday. And when you get time, I highly encourage you to look at the paper there that I co-authored with Pavel Curtis, who is architect in the Windows division. His team is among the first consumers of module implementation as in the Microsoft compiler, and some degree it also owns, not directly but indirectly, Windows.h, so they know a lot about macros, and they also know the pains of macros, and they strongly believe that macros should be contained. So the paper has a discussion about how we can handle macros while you transition into a better place. So the other thing that I wanted to touch upon before I take questions is the fact that modules for C++ are an enabling technology. It allows us to do things we couldn't do before. It's not just about build throughput or compile time. If all your worry is about compile time, that's a one-time thing. What do I mean by that? Once we've made the compiler go faster, done. There is nothing else that will come after that, right? It's a one-time thing. However, if you look at other aspects as componentization and semantics-aware developer tools, that is some kind of gift that keeps giving, right? It opens the door to scenarios that are very painful to get. Start with very simple things like we all have on our platforms some form of loading dynamic libraries, right? If you're on POSIX platform, you have DLSim and DLPen, DLSim, and if you're on Windows platform, you have load library and get procs and that kind of stuff. But if you look at the practice, it is it's very unsafe, right? You have to know in advance what it is. You get some void star back, and then you cast. Trust me, I know what it is. You reinterpret cast to function type before you call. We should be able to do better than that. We should be able to tell the linker, oh, please give me the symbol that has this type. And if it's non-existent, then throw an error. Today we just say, oh, give me that thing and some string, and then crossed fingers, right? So you will be able, for example, to have type-safe, completely type-safe dynamic loading and resolution of symbols. If you're in an environment where you have to glue several components together, not written in C++, not all of them written in C++, usually have wrappers, some of them automatically generated and that kind of stuff. It is possible with modules to get that in a type-safe way. Why? The reason is extremely simple. Any production-grade implementation of modules will have to store, to persist module interface in one form or the other, and they will have to persist declarations, types, and so forth. So that's the information that's available. And you can leverage that information to automatically generate type-safe wrapper. You don't have to cross your fingers. And that allows you to actually use type-rich interface at system APIs level, right? Today, when we use C++ for system programming, now C++ is designed for system programming. Most of the time, the APIs will be external C something. We we say, hey, we're using C++ because, it's powerful, it allows us to have the right abstractions. But the minute we have to do the right, the real work, we drop down to the C level, right? You can have the C++, the type-rich C++ abstractions because you have the descriptions of your exports, complete description embedded in your module interface. So it's an enabling technology, and we should seize that opportunity to bring something new to the language, not just build throughput. Now we have software architecture aspect. We have semantics-aware tools. We can build that. Some of them we're building at Microsoft. My hope is that the larger C++ community will coalesce around this, recognize this opportunity, and be serious about it. So, I don't have a lot of time, but I'm going to, again, as I'm pushing this, I want to start a conversation with something concrete, right? And then get the community. You don't have to agree with it, but if you disagree, I want to understand your technical objections or things that need to be added or removed to improve. But just not doing anything shouldn't be an option. We should be able to do more than that, right? And it is possible. So at least in the Microsoft compiler, when you compile module interface, it produces metadata that is stored on disk. In the current release of the compiler, we haven't documented that format. We are in the process of making it less Microsoft specific and be Microsoft neutral because we want the larger community to realize this opportunity and coalesce about this. Just take it as initial inputs, and we can throw it away, replace with something. That's fine, but start the discussions, start the thinking about this, and build something that we've lacked for too long. We're using format. Essentially, like I said, any good production-grade compiler that implements C++ module is going to store the metadata that's produced out of compiling the module interface on disk in some form, right? It will be, in my view, disastrous if on the same platform you have n compilers using n distinct formats to represent the same information, okay? And I also think it will be disastrous if we don't see the opportunity to actually share information across platform, okay? So what I'm proposing is not a standardization of ABI. No, I'm not proposing that. What I'm suggesting is a shared data structure to represent information. Very different, okay? So if you have objections against standardized ABI, that's fine. But this is not it, and I will encourage you to keep, an open mind about the suggestion here. If we don't do this, it is an opportunity. We will let an opportunity pass by, and we'll have fragmentation of the ecosystem, tooling ecosystem around C++ and among implementers. The first thing is, C++ is very interesting in the sense that if you really want to present just, let's say, declarations, not definitions, just declarations, you have to deal with types and also expressions, constants, because we have templates. The template argument could be type, which most other programming languages have, but very few of them, if any, actually allow you to use arbitrary expressions, with some constraints on as template argument. So if you're going to describe, let's say, student array of, my class and some value, you're going to have to handle expressions. The other thing is that templates are key cornerstone of the success of C++. The standard library is full of templates. So if you're going to export the standard library, you have to be able to represent template. And if you represent template, then, well, you're down to represent the entire language, okay? Now, when you compile your interface, the compiler has gone through, tokenization, parsing, template instantiation, that kind of thing. We call it elaboration. So a lot of resolution has already been done. It would be foolish to throw that away. And if you want to represent the interface, you have to represent the entire C++. So there is this notion that I call abstract semantics graph, which is what you get after you've parsed and analyzed all your input. It is not a tree, it is a graph, really. And when you do that, you must represent all C++ because you get templates and you get expressions and that kind of stuff. Fortunately, Binary Source and I looked at this problem about 10 years ago, more than 10 years ago. It was not directly connected to modules. We were thinking about something else at the time. We were thinking about semantics-based transformation of C++ programs, static analysis. And we developed this data structure we call IPR for internal program representation. And there is a description of it that we published in journal. I put a link in there. You click on the link, it'll give you a PDF to read. The source code is out there on GitHub. It is BASD type, license. So it is very permissive. And you can peruse it to get a sense of how we did it. And if you're a compiler writer, you will get a lot of surprises, except that we managed to have a very general description of C++. And it is important that we have a generalized C++, because otherwise you get to mimic all the complexity, the barnacles in the standard, and that's not a good way of representing C++. Okay? And we have very, fairly good coherent design there. And it is the abstract semantics graph. So the implementation that we have in the Microsoft compiler essentially has the IFC format. When you compile an interface, you get an IFC format. So essentially you get a signature, 4 bytes. Then you get a header, and that gives you how to get information. Then you have table of content, the summary table of content, and then you have partitions. So partitions are essentially the representation of the entities, types, declarations, expressions, statements, names, all this kind of stuff. I won't go into too much detail because first, I don't have time, and second, the details are still evolving, but this structure has remained the same for the last 12 or 18 months, and I don't expect it to significantly evolve in the next 12 months. But the details of each partition is going to evolve. So in the header, you have version, both minor, and you have 2 bytes for version, and you have API information, and you have architecture that's targeted, and then you have an offset that gets you to the table of contents. And the table of content is pretty simple. You get the name of the module, the name of the source file that contains the module interface, and the other thing you get is what is the first declaration in the global scope that is exported. Every exported entity in a C++ program has a root from the global scope, right? If it's in a namespace, then you have to define your namespace, which is in the global scope, right? So you start from there, and then you walk the entire thing. And the number of partitions, so what we call partitions, is just a homogeneous table of entities, right? So you always have the string table because you have to store strings, the name of the modules, source path. So the string table is always there. And I won't get into the details of the partition at this point, but from now and till by the Visual Studio 15, VS15 RTM timeframe, I will put out a version, let's say 0.5 or 0.9 version of the IFC format to the community to comment on, and hopefully embrace. If you want to throw it away, design it, that is fine. But I want to see the community, active in that area. And so, like I said, the partitions are just homogeneous tables of things. So they have names. So the partition has a name, again, declaration of variables and so forth. And that is basically all. I'm ready to take questions.
Hi, I'm interested about templates and how the user has to export them and how the implementation could improve compilation times and basically everything related to that.
Okay, great question. So the question is, how about template, how user get to define a template and how module helps improve compile time. So to export a template, it is just as easy as any other declaration. Just stick the keyword export in front of template, you're done. Now, the next thing on the compiler side, what the compiler does is it goes through the definition of your template and has to remember which names which declarations are referenced in the scope and build enough data on the side so that on the import side, when the template is instantiated, it goes and abide by the existing rules. It is work on the compiler side, but it is ordinary work. Okay. Now, how does this actually help build throughput? The first thing is you compile your interface once. So all the information has been processed once and stored on disk. If you import your module and you never use the template, it never gets instantiated. It never gets parsed again, right? Only its name is there for the compiler to know that it's a template name, so that you can do parsing. You know that in C++ you cannot even tokenize correctly if you do not know the set of template names, right? It's kind of strange. Now, in most programs, for example, will have something like vector of int or vector of size t or something like that, right? So there you have an opportunity, the compiler has an opportunity to actually share an instantiation across usage of module. So we have this thing in standard C++ 14, I think, or 11 or 14. We have extern template, where as a library writer, you know that you're going to have certain instantiations come up very often. You go out of your way, you say extern template vector of int, something like that. And then in a separate file, you have to have explicit instantiation, and you're just telling the compiler, oh, this is going to be used very often. I'm going to provide definition out of line, and if you want to instantiate this thing, go ahead, but don't work too hard. With modules, you can have something similar, just say export vector of int, and that has the same effect, except that you do not need to worry about having to instantiate on the side. So if in your project you have certain template that you know you're using very frequently, you can use that mechanism to reduce the instantiation time.
Okay, thanks.
Hi. Namespaces are essentially open-ended. Any translation unit that contributes more to a namespace, the namespace gets more symbols. I wonder, are modules the same way, or do you have to feed all of the modules contributing to all of the translation units contributing to a given module to the compiler in one go? Mm-hmm. And I wonder further, you said on a slide that there is a distinguished translation unit, and I wonder if you'd speak to that.
Okay. Yeah, so the namespaces by design span translation units. There is no bound to it. For modules, the initial design still has that in the technical specification. Says that for the list of exported declarations have to be given in at one place, in one source file. I originally put that restriction there so that we can focus on the biggest item. Right? It is possible to actually spread the exports over several source files, but you still have to give them together. The set of source files that make up modules has to be given, right? Because if it is the export, the compiler has to know. So imagine that you declare you export a template, a class template, vec, in one source file. And then in another source file, you're using vec of int. There must be a way for the compiler in the other source file to know that vec is a template, because otherwise it cannot even tokenize properly. So that's why you need to have this set of things that are exported in one place. C++ requires the parser to know something whether something is a type name or not. So all these problems come from the grammar, not something, well, other languages have different ways of doing it, but we're working in a specific constraint. What was the last point that?
You spoke about a distinguished translation unit.
The distinguished translation, that is the translation unit that contains the set of exported declarations. And as I said earlier, I hope to relax that requirement in future revision of the technical specification, where you can spread it over several translation units. Richard has a similar suggestion with syntax. I am on the side of no syntax, and we will hash it out. Richard and I will talk it out and talk to the committee, and you guys wouldn't have to worry about it.
Thank you.
Hi. As an extension to that question, kind of, when you suggest having a std core module, there's a lot of containers and a lot of basically mostly separate header files that are included in that. Would that be a single module, or would you imagine std core vector as the standalone module, like pretty much one per header, or how would that work?
My view is that you put all the containers together. Now, let me explain. If you're doing header files, then people will scream like, it's over inclusion, and it's going to slow compilation down. Excellent point, except that these modules are not header files. Concretely, when we import a module, the only thing that the compiler really does on import is just make certain names visible, because it has to know whether something is a template or not. It doesn't do anything else. If you do not use a container, it never gets rematerialized inside a compiler. So you don't pay for what you don't use. So you don't actually see the over-inclusion materialize in your code. So I wouldn't recommend it, but this is, it's a question to the community. Having to remember whether hash map is in hash map, sorry, it's not hash map, it's unordered map, and a set is in set. It's just, there are too many of them to remember. Just put them together, and most people say the STL.
Thank you.
Hi, Gabby. Could you please briefly comment on the relationship between modules and const-expr? And secondly, it sounds like we're going to have a de facto alternative, I'll put it politely, to a standard ABI. And could you maybe comment on how you foresee that working?
Okay.
Thank you.
So there is a restriction in the specification that says if you export a const-expr function, then you must also provide a definition for it in the interface file. So the same goes for inline functions. So it makes sense. Essentially, you're going to ask a compiler to evaluate the body of the function and give it a body there. There is no point in trying to hide it and ask the compiler to go and do magic to recover it. So I think your second question has to do with standard API.
Yes, correct.
So the format that I'm suggesting does not standardize API. What it is doing is giving you a description, a symbolic description of a C++ program. Compilers will continue to have their own API and how they generate calls and all of that. If they want to have int 2 bytes, fine. It does not standardize that.
Thank you. Wonderful.
It's purely symbolic.
What are your thoughts on supporting legacy code which still contains macros? There was yesterday a nice presentation on this, having an optional support in modules for macros. What is your take on this?
Please, I didn't catch the beginning.
What are your thoughts on supporting legacy code? I like your vision for the future, but our code bases today are different, and we still have to, see how to support them. Okay.
Yeah, very good question. The design is there, and we're here. How do we get from there? So first thing is what we really call legacy code. Those are full of macros. My suggestion is leave them there. I hear people say, oh yeah, you must be able to get modules there without modifying the source code. I don't actually think that is true. I've seen the talk by by manual yesterday, and one of my takeaways, well, you still have to modify the source code some way. Now, not all legacy codes are bad. Many of them are, the header files are modularized. If you take the standard headers today, they are well modularized, as Richard pointed out yesterday. And there, in the paper that I described, I pointed out, you actually have a mechanism of automatically generating IFC's module interface metadata out of header files. And if you happen to have macros that you need to export, then you actually have the IFC, and then the compiler generates a wrapper header that says imports that module, and then put the macros that you need to export out. So, you don't have to invent a new syntax for macros with modules to get macros. And that is the approach that has been used so far in the in the Windows division. And how to do that is in the video that I link to the in the talk.
If you have a module consisting of many translation units, is it true that you'll need to use header files within those modules to handle any inter-module relationships?
Okay, so the first thing is, if you have the interface file that declares, export, defines certain types, then every single definition or declaration in that interface file is visible to all the translation units that are part of the module, whether that declaration is exported or not. So you do not need header files to communicate those informations to the components. Now, there is the question of, what if I want to share some information that I don't want to put in the interface file, the source file that contains all the export, but I only want to share between two translation units that are part of the module. So far, the solution that have been suggested is to use submodules. They're essentially as modules, except that only those two components know about them. I don't have a complete solution. I know that other languages like C# have framed assemblies or kind of that. I don't know that's the right approach, but the submodules approach works well.
Yeah, you mentioned some new and interesting things coming in Visual Studio 15. I'm a Visual Studio user, right, day job. I'm wondering if the intermediate format that you're proposing, is that going to start to make its way into Visual Studio's developer experience with a static analyzer or refactoring or any of that stuff, or is that still sort of forward-looking?
So it is essentially forward-looking. We were starting from there. This is what we have. We're going to have the documentation, and we would love the C++ community to develop to the ecosystem around that. Yeah, clearly, Visual Studio also comes with static analysis, and we will have to work with that. The same for the PDB and all kinds. So it have to roll out in stages. So you can think of this as development in the open, even though it doesn't seem that open to you. It is really development in the open. Okay.
All right, thanks.
Hi, I've got a question about the uniform representation of the AST3. As I do understand, it contains some unoptimized version of the library. Are there any plans to create an optimizer that works with that uniform representation and make that optimizer open source?
Okay, so the representation that you have doesn't take into account optimization, because it doesn't need optimization. It is optimization agnostic. When you import the module in your source file and you have some optimization level set, then the code generation is done from that representation. So whatever optimization you set is going to have the effect of generating code from there. So there is no problem of mixing it's not like you have machine code unoptimized plug into your optimized code. No, you have a symbolic representation of the input source code that is used as input to the optimizer to generate code at the point where you actually import the module.
Thank you.
So I just want to double check my understanding. Your proposed format, is it supposed to be isomorphic to C++, the language?
It is supposed to, the way I would characterize it is an alternative way of representing program for the C++ abstract machine, right? That's it. So you can compile your input source code to a representation of what the abstract machine is going to execute. And that representation is far more general than standard C++.
And so that means you could, in theory, feed that format into the compiler instead of your source code.
That's right.
Which would mean we could, in fact, get an alternate syntax for C++ that compiles into that format.
Exactly that. And as a matter of fact, Bianin and I did that experiment 10 years ago, where we call XPR. So we have the IPR, which is the internal representation, and you have the XPR, which is the external representation, which is an alternate representation of C++ program. Most people think C++ is defined by its syntax. It is not. What is important is the core semantics, what the abstract machine understands.
Thank you.
Richard?
Hi, Gabby. So it seems to me that there's a fundamental tension between the needs of different compilers in IPR. For instance, some compilers' internal representations will only have one entity representing all of the redeclarations of some particular function, and other compilers will represent all of those distinctly. In order for them to share a format, it seems like something's got to give there, that either one of the compilers has to maybe change its internal representation to store that extra state, or the other compiler has to cope with information that it needs simply not being there. Do you have any thoughts on how to address that tension?
That's an excellent question. So the IPR is not intended to be the internal representation of every C++ compiler. As a matter of fact, it is not even the internal representation of the Visual C++ compiler. I can tell you that because, well, as in past releases, we didn't have ASC, right? So it is not intended to be the internal representation for the compiler, but it is the representation on disk, the persistent representation. So the thing that will come with the format is a set of APIs to work over that, right? So if you want to expose the IFC to your program, you can expose that through the set of APIs. But as a compiler writer with your own representation that you love, you can just, when you're writing the IFC out, you can just map it. You don't have to change your representation, just map to the...
Okay, but my concern is the case where the compiler producing the IPR does not retain some information that the compiler consuming the IPR really, really wants or needs as part of its invariance.
That
seems hard to solve.
Yeah, and that's why I want the implementers community to be involved to ensure that we get it right. My view is that when you do the IPR, when you get it right, you actually have to some degree, a formalization of the language that's understood by the C++ abstract machine. And if something is not there, all of inventors being in the same room working on it, we should get it. We should nail it down. Thanks. That's an excellent question. Okay, I will take one last question. I'm told that over time.
All right, I don't know if this is worth being the last question, but what about conditional compilation? Sometimes, you mentioned Windows.h, and I know what's in there, and a lot of that is to deal with platform-specific variations.
Yeah, so whether it is Clang or MSVC or in general, you're going to have what we call configuration parameters. You set a configuration that you use to compile the interface file. And compilers will have mechanism to map that and to the IFC. I think today, for example, Clang would check whether the configuration parameters are consistent. The same will be true for Visual Studio.
Okay, thanks.
Thank you very much.